Hello, my name is Knut Benedict and I would like to tell you today something about stopping capability, stopping dynamics of ships. And I will use this wonderful SAMMON fast time simulation software here, so we can do much more, can get much more information than you have normally on a ship in a wheelhouse poster or in a maneuvering booklet where you might have graphs or drawing like this. We can do much more better with this kind of software. It's the same quality as in a ship handling simulator and even better, but fast time simulation means we see every result in a finger snip. So we have chosen as a ship, we have chosen cruise ship with twin screws and twin rudders, both thruster, stern thruster. And the ship is located out of the port area of Rostock, which is our wonderful home port and wonderful port home of our Department of Maritime Studies. And we have located the ship on the anchorage. So we use this one as a center here, and we enlarge the picture a little bit up to this scale. So this is a ship here. And first we want to discuss the standard stopping capability as crash stop. So this is the same what we have in a maneuvering booklet, and this is the only one which you have there. For this reason, we give the ship a certain speed and we start our discussion with full ahead. So the engines are synchronized and the ship is going there with a speed of now 22.3 knots. And the fast time simulation provides the position of the ship every minute up to 24 minutes ahead. For the time being, it's 6 minutes. And the good thing is, if you want to see what happens on this track, then you move a reference position, like here, which you can click every 10 seconds, for instance. So now the ship is moved into second position after 1 minute, and this is the position where we will start our stopping maneuver. For this reason, we put a maneuvering point, add a maneuvering point here, and then our focus is on that maneuvering point number 1. And here we can do the next maneuver, for instance, to reverse the engine as a crash stop. For this reason, we take the engine order and reverse it until minus 100% to full astern. What you immediately have seen is the shapes here, they have squeezed together because the ship is getting slower, 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 slower. And here is the final reach the ship has had. And then if you enlarge the prediction up to 24 minutes, then it pulls back. But we want to measure how long the stopping distance is. For this reason, we move our ship with this magic time slider to the position where the ship might have 0 speed. For the time being, it's 1.2 knots, a little bit more. So now we have 0.08 knots, nearly stopped. And we can read here the distance, 1653 meters, and it has taken 275 seconds. Okay, this is our stopping distance. And the first question is, do we have a certain reference which we can use to have our stopping distance at hand, maybe at even every speed that we can see in our sea chart or radar the stopping distance of our ship? Yes, we have. For this reason, I show you the use of the speed vector of a vessel. So I move the ship back in the starting point of the stopping maneuver here. And now we can adjust our speed vector. For the time being, it's 6. Now it's 3 minutes. And you see the speed vector is from here up to this tip of the arrow. So this is for 3 minutes the speed vector. So what we see is it's a little bit longer than our stopping distance, so you know the stopping distance is smaller than 3 minutes. We could even have some reserves. Maybe we don't go back to minus 100%. Instead, we go for maybe 50% only. Then you see immediately the stopping distance will getting a little bit longer. And even if you go back to 30% astern, then we see for full ahead to 30% astern, the speed vector has the same length as our stopping distance. So you have a sort of reference which you can use if you steer your vessel. Okay, so this is for full ahead to astern. What happens if we have a lower speed, maybe 60 knots? For this reason, first I go back to the reference position, the first one, so maneuvering point 0. And for this one I can add, so select edit, I go back to the first situation. Here we had 22 knots. I will reduce the initial speed to, let's say, 70%, then we have 16.9 knots still as initial speed here. If I go now to the next position, then we see what happens to the stopping distance from 16.9 knots. So I go now to the point number 1, and then we see, okay, with full astern, 100% astern, we have a stopping distance which goes up to here. So, and this, by the way, the speed vector of 3 minutes is still a little bit longer than our stopping distance. So it works, because if the speed gets smaller, the initial speed here, then also the speed vectors goes shorter, and the stopping distance is shorter. So it's related to each other, so you can use this reference. And to measure the distance, I will move our reference position again to this position. So here the speed is nearly, no, this is too much. The speed is half knot. So here it's exactly 0 speed, and the stopping distance is here only 1,132 meters. And the stopping time is 230 seconds. What we can achieve when we move this reference position, we can, for instance, I move it back up to here. So you see still the engines are going full ahead with 100% pitch, RPM 95 revolutions per minute. But when I move this ship out here, then you see the revolution goes down. So then we have the situation where the engines are stopped, and when you increase the time, then you see that the engines are starting in reverse mode. So you can see every different position. On top of that, we have seen that our stopping distance is smaller than the 3 minutes. Also here we could use less astern, like 50%, 30%. No, this is 10. This is 30%. So we are still smaller with our speed vector. Here we could even go to 20%, and that is the same, nearly the same distance. Okay, so let's get back to this situation. And the question, so this is the initial position is now, it's 16.8 knots at this position. And this is our stopping distance with full astern. So we can see it here. But the question is, could we shorten our stopping distance? Could we achieve a smaller stopping distance than these 1,100 meters? Yes, we can. We increase the resistance of the ship using the rudder. So immediately you see the result. If I move the rudder, for instance, to 5 degrees, 10 degrees, 20, 30, 25, this is 35 degrees of rudder. So what you immediately see is the so-called advance, that means the distance in the ahead directions, is much more smaller, nearly half of the distance. So the only disadvantage is that the space, maneuvering space, is now getting bigger because of the transverse motion of the vessel. So you see the ship would go until here and then it pulls already back. After 3 minutes it has reached nearly its maximum distance. If we want to stay on that track, because we are in a narrow waterway, we cannot allow for any sideward motion, then we might think about why not using the rudders as we see it here. Now the rudders are both to starboard, but why not using the rudders instead, one to starboard and one to port side? So for this reason we take the we have to desynchronize the rudders. So this rudder is to 35 degrees and this rudder is going to minus 35, that means to 35 degrees to port side. So what we see is the ship is going straight because the rudders are spread outside, and the stopping distance, only to measure the stopping distance, is now here 1000. So we are 100 meters shorter. This cruise ship is extraordinary because it has high lift rudders which you can spread until 70 degrees, 70 degrees. If we do this, the one to port, one to starboard, so you see that the distance is even shorter. So it's now only 800 meters. So you can gain a lot of quality in stopping if you know about all the maneuvering capabilities of your vessel. And there's another option, because this ship has twin screws. So it has 2 engines and you can operate 2 engines separately. So we will forget about these rudder activities. I switch the rudders to a midship. Come on, to a midship. And the idea is to use the engine already on this track. When we go along this side, we already adjust one engine to astern. So it's slightly going astern, then you avoid the reversing time of the engine which you need. So we have seen that it takes a while until the propellers are working in a stern direction. And so in this position number 1, I go back to the initial position here, and the 60 knots which I have here, we don't do with 70% of both engine in head, but instead I desynchronize the engines, and so I can pull one engine back maybe to only minus 10%. So you see immediately, okay, the ship is getting slower. It's getting now 11.9 knots, but if I increase this engine to full ahead, so we are on 16.3, so it's nearly the same as we had before. We had to adjust the rudder a little bit because this starboard engine is braking, so we have to adjust the rudder a little bit to the starboard side. Let's say this is 1 degree. Okay, playing around a little bit. So this is where the ship is going straight. And we can move now into this position, and we arrive here after 1 minute with 16, no, it's not, it's a little bit adjusted, sorry for that. It's about 15 knots when we arrive here because the engine is a little bit adjusted. But what we see here is the stopping distance is much more smaller. So I move the ship up to our reference position here, where the speed is 0, like this. So this is exactly, it's 900 meters only. So what we learned from this is that if you are thinking ahead and you use your engine here already, one engine is already well prepared, is going already astern. If you then move both of the engine asterns, as we did here, then the stopping distance is shorter than in contrary if you use at this distance both engines ahead. So I hope you understand these principles which we were talking about. So we have learned that we can use our speed vector as reference for the stopping distance. We have learned that so smaller your speed is here, so shorter is your stopping distance. Okay, this is very simple. Then we can further reduce the stopping distance by using the rudder. With twin rudders, you could even spread these rudders to increase the resistance. And the fifth measure was that we, in case we have a twin screw vessel, we can already operate one engine astern. Then you are well aware if you have to stop out of a sudden, then you can shorten your stopping distance. And maybe you could even combine all of these parts, even to this one, that we use the rudders to further reduce our stopping distance. So we have any options we could do. In this case, sorry, I used the rudder to the wrong side and to the other side. So this is our smallest stopping distance of about less than 700 meters from 15 to 16 knots. Okay,